All right, so now we're going to look at a vector function. So instead of just a vector like 2, 3 or something, the vector is going to be a function. So I'm going to have the vector s be equal to sine of 2t cosine t. I'm going to put vector brackets on it so I know it's a vector function. So sometimes this would be called a vector valued function. And that's because not everything about this function is a vector. The independent variable, the domain variable, is a real number. It's the range variable that is a vector. So this vector function takes a real number t as an input and outputs this vector. So the ranges are vectors and the domains are real numbers. All right, so usually the real number is representing time. All right, so here's a function that represents certain vectors, okay? Now, if it looks familiar, that's because it's this one. Remember this one? All right, so what happens is that how we're looking at these, if we're looking at these parametrically, right, this up here is parametric function. All right, but if I look at the vector function, all right, if I look at it as a vector function, this is the vector sine of 2t cosine of t. And how the vectors really work on here is that, you know, for t equals 0, I have this vector. And for t equals 0.3, because remember these counted by 0.3s on the points, that's this is vector 0.3 right there. Right, and then there's this one's vector 0.6. So the vectors sort of go around like that, always back to the origin. But what you really want to think about is that this is a point in space, and your book sometimes sort of doesn't even make a distinction between the original function, whether it's a vector or a point. It sort of treats them the same way. So you want to think that this vector is giving position. It's really acting like a point. So what's really acting like a vector is this. What we're now able to do is say, how fast is this thing going? So we were able in the past to say what is the tangent, which is really in what direction it's going. Now we can say, how fast is this thing going as it goes around here? All right, well, guess what? It's just the derivative of the position. So the velocity is equal to s prime, so vector s prime of t we could put there. And so for this function, that is 2 cosine of 2t, comma, negative sine of t. Yeah, and then, of course, we can also say what the acceleration is. That is s double prime, but now s is a vector, so we're doing the derivative of this vector. So I'm basically just doing the derivative of this, derivative of this. So the derivative we say component-wise, so we can do the derivative component-wise. So that means component by component. So if I had 3 components, by the way, so a 3-dimensional vector, I would just do the derivative of all 3 of them. All right, so we're doing 2-dimensional vectors. We just take the derivative of sine of 2t as 2 cosine of 2t, derivative of cosine t is negative sine t. And then we do the same thing for our second derivative. So we're going to end up with negative 4 sine of 2t and negative cosine of t. So what these are is the acceleration and velocity vectors. So let's see what we can do with this. So let's look at what would s of pi over 4 be. So I'm just picking pi over 4 as a time. And I've also remembered to switch my calculator back to radians, by the way, because I'm using radians now. All right, you just have to be aware of what you're using when. So my position at pi over 4, since I'm doing sine of 2t, cosine of 2t, it's just going to be sine of pi over 2. Cosine of pi over 4. And of course I could, call those 1 and square root 2 over 2, but I want to look at sort of the graphs. So this vector is 1.707, so I'm going to use decimals to represent these vectors, even though as using pi over 4 I could get exact values. All right, but I want to plot them, so I want decimals. So the vector, so the velocity at pi over 4, so I was using v before just for vector. Now in this context, v is velocity. All right, maybe I should write that in here, that this is position, velocity, acceleration. All right, so velocity of pi over 4, I'm just going to plug in some, I'm going to say it is the vector 2 cosine of pi over 2. So I'm just plugging pi over 4 into here, and then I get negative sine of pi over 4. So as a decimal, that is 0, negative 0.707. And then I can look at the acceleration at pi over 4. And that one's sort of a little weird, but you'll see sort of how it works. It is negative 4 sine of pi over 2, comma, negative cosine of pi over 4. All right, so I'm just plugging into there. So that's going to be negative 4, negative root 2 over 2. That's the acceleration. All right. Now, other things that I can get here is the speed. So speed, just like in real number context, speed is the absolute value of velocity for real number functions. For vectors, speed is the magnitude of velocity. So I can find the magnitude of the velocity, or the speed, at pi over 4. And that would be equal to the square root of 1 squared plus 0.707 squared. So 1 squared plus 0.707 squared. And that happens to equal, oh, I don't know what it equals. Let's find out. That's one of the things I did not do ahead of time. All right, so it's going to be square root of 1 plus 0.707. You know, I could be more accurate with that, but I don't feel like it. It's about 1.225. So 1.225. That's the speed, for what it's worth. So notice that position, velocity, and acceleration are all vectors, but speed is a scalar. All right? So these are all vectors, but speed is a scalar, which, remember, in this context just means it's a real number. It's not a vector. All right. So I think we can... Yeah, let's plot these on here, and then we'll look at this in more detail in the next video. So I'm going to go ahead and put this one on here. So my position is 1.707. So I'm going to just go to 1.707. It's probably going to be right about there, right? And I'm not going to draw the vector to it, like we can imagine the vector, but it's really just telling you where you are. So it's the position. Okay, what is our velocity? Our velocity is 0, negative 0.707. So 0, and let's see, negative 0.707 means I'm going to have really the same length as what we are here. So it's going to, actually it's going to go all the way back right down to the x-axis. So our velocity is like this. All right, so now look, the length of that velocity vector, hey, I did the speed wrong. Because the velocity is 0, negative 0.707. Oh, geez. Okay. Does that make sense? All right, so the velocity was actually, I used the position instead of velocity. Velocity, which is 0 squared plus negative 0.707 squared, which obviously is going to be 0.707. So what keyed me into the fact that there was an error is the speed is the length of the velocity vector. So I can see here that the velocity vector is 0.707, and that number is not 0.707. So that's how I knew that the speed had to be wrong. So here's our velocity vector. So things you can notice when we're at this corner point, all right? So what are we doing? We're going around this thing. So you can really think about the dynamics of motion here. So you're going around this graph. When you're coming down to this point, your direction is that you are headed straight down at a speed of 0.707 units per linear space units per time unit. So meters per second or centimeters per hour, whatever it is, we don't know. All right, but it's space units, linear space units per linear time unit. All right. Now, what about the acceleration vector? Where's the acceleration vector? So the acceleration vector is -4, negative root 2 over 2. So negative root 2 over 2, I don't know why I left that one like that. It's also 0.707, right? So it's actually negative 0.707. So the y component of acceleration is 0.707. It's the same length as this, right? This is the y, so it's come about to 0.3-ish. This is the x component of acceleration. But the y component of acceleration is 4. So remember, this is 1. So to go 4, we have to go like 1, 2, 3, 4. And we're going to be way down here somewhere. So approximately here-ish is the head of that vector. So the acceleration vector is like this. All right, that's acceleration at pi over 4. All right, what the heck does that mean? So what this means is you are accelerating very strongly downward and a little bit to the left. All right, so what's that about? As we come around this corner, okay, we're trying to make this corner. So we have to, like we've been going this direction, we have to start going this direction. So it's our attempt to turn, it's our curving, our attempt to turn that causes this huge acceleration in the negative y direction. And the fact that we are still slowing down, right? So we're slowing as we went to the right, and we're accelerating downward. So that's why we have a sort of a moderate negative component to the left and a huge component down as we're coming around this curve, because that's the force that's required to bend our velocity vector around like that. All right, so those are kinds of things, dynamics of motion that you can think about as we go forward. We're going to look at a couple of more velocity vectors on this graph next.